Hello and welcome to Chapter 5, Lesson 1 on the history of the atom. Now, when I say the history of the atom itself hasn't changed since the universe began. What I'm talking about really is the history of our perception of the atom. So I'm going to start here in 1808 with John Dalton. Now, there were other thinkers who thought about the atom before 1808, but really, their models of the atom pretty much align with Dalton's. Dalton just kind of wrote it down and formulated the rules and really started the discussion among the scientific community. And he experimented with gases to formulate his laws. So he was also one of the first to really do a lot of experiments surrounding the atom. So he determined that atoms always combine in whole number ratios, right? So you would never just see like 1.37 atoms bonding to one atom. It's always 1 to 1 or 2 to 1 or 2 to 3, something along those lines. And so because he saw that atoms always combine in whole number ratios, he concluded that atoms can't be broken into any smaller pieces. So he said that there was nothing smaller than an atom. And that's where we get this idea of these sort of billiard balls, right? So there are different varieties of atoms, just like there are different varieties of billiard balls. There's the 1 ball, and that's yellow. There's the 2 ball, and that's blue. There's the 8 ball, and that's black, right? So you can tell certain atoms apart, but they pretty much all behave in the same way, and they can't be broken apart into anything smaller, right? And they can be bigger or smaller, the balls themselves, but they're not much different in the ways that they behave. Now we're going to learn, of course, that is incorrect. So let's watch this experiment here called the cathode ray tube, and this was first done in 1897. So there's no audio coming from this video, so I'm just going to talk over it here. What we have here is a tube that is completely empty, right? So there's nothing in it. It's a vacuum tube. There's no air. There's nothing else. And on either side, we have two sides of a current, right? So we have a cathode and an anode. And when we start this current, right? When we put power into it, watch what we see here. So we know for a fact that there's nothing in the tube. And that was very confusing to scientists because they thought that there had to be something there to conduct the electricity. But we knew there wasn't. So this beam has to be something new, some kind of new particle that's shooting along the cathode ray tube here. So now what our demonstrator is going to do is he's going to put a magnet up to this beam of new particles. In just a second. So we can see that one end of the magnet repels the beam, and then he's going to flip it around. He's going to flip it around any minute now. So he flips it around, and you can see that the other end of the magnet attracts the beam. So the end of the magnet that repels the beam, that is the negative end of the magnet. And the end of the magnet that attracts the beam is the positive end. And so we know that opposites attract. And so we know, therefore, that this beam is made of negatively charged particles. But J.J. Thomson, who was conducting this experiment, did more than that. He was able to weigh those particles, and he was able to determine that they weigh about 1/2000th of a hydrogen atom. So in other words, these are particles, negatively charged particles, that are much, much smaller than an atom. And those are called electrons. So J.J. Thomson in 1897 came up with what he called the plum pudding model. He discovered these tiny negatively charged particles that weigh much less than an atom called electrons. But he knew that atoms were neutral because if atoms weren't neutral, there would be a lot of problems, right? But we would be able to detect that there was a charge on just everyday objects if atoms were not neutral. And so if the atoms are neutral, which we know, but if they contain these negatively charged particles, then there must also be something positive somewhere that's balancing out that negative charge. So J.J. Thomson's idea was that the positive charge was just surrounding all the negative charges. And the metaphor he used was plum pudding. So this looks just absolutely disgusting, by the way. I'm sorry, but you could not pay me to eat this. This looks gross. If anyone out there loves plum pudding, I apologize, but I don't. So anyway, in this metaphor, the pudding is the positive charge, and then the individual plums are the electrons. So these electrons are just sort of sitting in this ball of positive charge. And we can see a close-up version of this model for the atom here. So you got our sort of soup of positive charge, and then these negative electrons just sitting around in it. Now we come to the gold foil experiment, which was conducted by Ernest Rutherford in 1911, and this is one of the most ingenious experiments of all time. And truly, this is one of the most important experiments, not just in chemistry, but in the entire history of science. It's really incredible. So what Rutherford did was he used a radioactive source to shoot these positively charged particles called alpha particles at a very, very thin sheet of gold foil. And when I say a very, very thin sheet, I mean about an atom thin. And so what we would expect, based on Thomson's model, where we've just got this ball of positive charge and these tiny negative charges throughout, what we would expect is that the positive alpha particles should bounce off those balls of positive charge and they should be returned to the alpha particle emitter. But that's not what happened. What happened is that 99.99% of the particles went straight through the foil to the other side, and only a few of them actually bounced back. And when they bounced back, they didn't always bounce straight back either. Sometimes they scattered. And so this was really wild, right? Imagine that you have a tennis ball and you're throwing it at a brick wall. And you expect, of course, for the tennis ball to bounce back at you. And then you keep throwing the tennis balls at the brick wall and they just keep going through the wall. And then you do this 1,000 times, and on the 1,000th try, one of the tennis balls bounces right back and hits you in the face. This is incredible. This is unbelievable. Because what this proves is that the atom is over 99% empty space. So everything around us, everything we see, is over 99% empty space. That is unbelievable. And this is a remarkable discovery by Ernest Rutherford. So in 1911, Rutherford comes up with his nuclear model of the atom. So if there was only, if it takes a positive charge to bounce back these alpha particles, then Rutherford concluded that the positive part of the atom must be very, very small and very, very dense because of how infrequently the alpha particles actually hit that positive charge. So in other words, Rutherford's model has this small, positive, dense nucleus at the center of the atom, and then there's a lot of empty space, and then there are electrons around the outside orbiting it that make up the outer boundary of the atom. And so those alpha particles can just pass right through. They can just barrel through those negatively charged electrons on the outside, no problem, because that's mostly empty space, and the electrons are very, very tiny. But if they happen to hit the small, dense, positive nucleus, that's when they would bounce back. But there was very, very small chance that they did because the nucleus is so small. Now, Rutherford ran into a slight problem, which was that the masses didn't always match the charges of the atoms. So atoms started to get bigger without necessarily having more positive charge at the nucleus. And so he enlisted the help of his colleague James Chadwick. James Chadwick did another experiment involving more radioactive material, and he determined that there must also be neutral particles in the nucleus. So Rutherford and Chadwick together now have determined that there are two types of particles in the nucleus. We have positively charged protons in the nucleus, as well as neutrally charged neutrons in the nucleus, and then around the outside, orbiting the atom, are the electrons. So, that is all for the history of the atom for now. We will pick it up again later, but for now I hope you enjoyed the video, and I will see you next time.